First of all, just a reminder, next week I won't be here. Okay. So there's a link to the video that you need to watch for chapter 6. And then when I do come back the week after, we'll review for the next exam. Okay. And when next week, there's no lab, so all you have to do is the lecture video. And the following week, we'll do the lab on separating binary mixture. Today, we're going to do the density lab. Let's get into chapter 5. Last week in chapter 4, we introduced the concept of the chemical bond and started off with the ionic bond. And covered naming compounds. Okay, so the 50 ways to name your compound. By the end of today, you'll be able to do all of those in that extra credit. 50 ways to name your compound. So we're going to focus on the covalent bond today. And I'll skip that for now. Key differences between the ionic bond and the covalent bond is where are the electrons? And we're specifically talking about the valence electrons. Those electrons in the outermost shell, yes, the outermost shell, that are available for bonding. Remember, you have the shell, subshell, and orbitals. Anything with the same principal quantum number is a member of the shell, the outermost shell. So those are the valence electrons, and they're the ones that participate in bonding. They either transfer completely from one atom to another, in which case you end up with an ionic bond, or they're shared between two atoms. Covalent bonds form between nonmetals. So we could have carbon and nitrogen form a bond, sulfur and oxygen, arsenic and bromine, phosphorus and oxygen. Any of those nonmetals can form covalent bonds. And another notable difference between the compounds that are ionically bonded and covalently bonded is covalently bonded compounds form molecules. They're discrete units, so they behave independently. Whereas ionic bonds are collections of ions, cations and anions in a matrix. And the way we express those compounds is in a formula that is the simplest whole number ratio of ions in the compound. All right, there we go. Ionic compounds are always solid at room temperature, whereas covalent compounds can be any one of our three phases, solid, liquid, or gas. Let's see, an example. Let's see, how about, well, the gases should be fairly easy, like nitrogen, dinitrogen monoxide, 2 nitrogens, 1 oxygen, that's laughing gas. Or another compound, say, well, at room temperature, how about octane? Octane is formed from carbon and hydrogen. It's a liquid, right? And you burned a bunch of it to get here in your gas tank. And then solid, how about a solid covalent compound? No, nothing comes to mind right now. How about diphosphorus pentachloride? That should be solid. Those are all covalent compounds. if we put a covalent compound in solution, usually we're talking about aqueous solutions here, just to keep it simple. Usually they're non-conducting. Not always, but usually they don't conduct electricity. So they're non-electrolytes. Whereas if you dissolve an ionic compound in water, it will always conduct electricity because you've got those free cations and anions to allow the movement of current through the liquid. Now, solid ionic compounds like solid sodium chloride, say. I've seen crystals that big that were grown from sodium chloride. And if you put a positive electrode on one side and negative electrode on the other side, you won't get any transmission, no current flow at all, because those ions are locked in place. They can't move. All right. Okay. So we get these shared electrons and in a covalent bond. And the simplest example is dihydrogen. That bond is between two hydrogen atoms. And remember, hydrogen is still an element, but it's diatomic. In other words, at room temperature and 1 atmosphere pressure, hydrogen is going to be H2. Right? Remember those on your, the ones I wanted you to learn? Those are the diatomic elements. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are all covalent. They're not compounds because they're the same element. They're just diatomic elements. In order to have a compound, you've got to have at least two different elements connected to one another. So carbon dioxide would be a better example for a covalent compound. But the bond is formed. What we're trying to illustrate here is that the one electron from one hydrogen is donated, another electron from the other hydrogen is donated, and a single bond is formed. And bonds, single bonds are always two electrons. So if we have these hydrogens, and I would write it like that, that's two electrons. So one line is two electrons to form a bond. If we have oxygen, it's going to have two single bonds or a double bond, and it has four electrons that are being shared. Okay. Nitrogen would have three bonds or six electrons, three pairs of electrons to form the bond between two nitrogens. Carbon dioxide is like that. So it's two bonds on one oxygen and two bonds on the other oxygen, two shared electrons. Oh, one other point. When a bond forms, the driving force for the formation of a bond is more stability. In other words, the bond between the two atoms makes them as a whole more stable. So we're talking lower energy. So as you form the bond, you get lower energy, and typically what happens is when the bond forms, some of that energy has to be released. Right? It's not stored in the bond somewhere. You release the energy, and that means it's exothermic. All right. So what happens, the other way to look at it as a driving force, aside from lower energy is more stable, is the tendency toward noble gas configuration. So when we form this bond between two hydrogens, and if I write it like they did, like that, now this hydrogen, I'm going to anthropomorphize. This hydrogen thinks it has two electrons, right? This one thinks it has two electrons. Well, what other element has two electrons? Just one single element, one single atom, helium, right? So each one looks like helium with two electrons. It's a completed 1s shell. Okay. So the tendency toward noble gas configurations upon sharing electrons is another way to think of the driving force for the reaction. Come on, there we go. So a covalent bond occurs when there are shared valence electrons between similar or identical atoms. These would be identicals, would be sharing, and these would be similar, carbon and oxygen. They're close to each other in the, they've only got nitrogen in between them. So they're similar, and they're always nonmetals. Now you can have metals that form bonds, but we're not going to introduce that one. That goes a little too deep for this course. And they form metallic bonds. But for now, metals and nonmetals form ionic bonds, and nonmetal and nonmetal form covalent bonds. Okay, when we draw the structures, we did Lewis structures last week, didn't we? A little bit. Okay. When we draw the structures, we step them up so that we account for all the valence electrons that are associated with either the atom or in the bond. So for this one, that's all you get, just the bond. For this one, you get a pair of electrons there and a pair of electrons there. And notice 2, 4, 6, 8. 2, 4, 6, 8. So each oxygen thinks it has an octet. And the octet for oxygen would make it look like neon. Nitrogen only has one pair over here. So 2, 4, 6, 8, or 2, 4, 6, 8. That nitrogen now has the appearance of an octet, and it's similar to or isoelectronic to neon also. For this one, carbon already has an octet, 2, 4, 6, 8. But these oxygens need those lone pairs. Lone pairs are non-bonding electrons associated with an atom. Bonding pairs are in here. So we have bonding or non-bonding. Non-bonding, sometimes we call them lone pairs. Okay. Now lone pairs, for now, don't worry about them too much. Just be sure that you've got either the duet accounted for or the octets accounted for when you're drawing structures. If you feel like getting more chemistry later, we'll find out that these lone pair electrons do contribute to the reactivity of these molecules. But for now, that's not a problem for you to deal with. All right, I mentioned single bond, double bond, triple bond, and each line represents 2 electrons. Okay, how many electrons are shared in a double covalent bond? Be 2 times 2 is 4. 4 electrons in a double bond. One of the convenient corollaries to tendency toward the octet is that specific elements tend to form a certain number of bonds. And that helps you create molecules more quickly and accurately. So we find that fluorine only needs 1 electron. It has 7 of its own electrons. 1 electron will give it the appearance of neon. So fluorine tends to, and all the halogens tend to only form a single bond. So this fluorine here would do like that. And then we would fill in the rest of the electrons here. Or if we paired fluorine with something else like hydrogen, fluorine would still only form one bond and hydrogen would only form one bond. So hydrogen has its duet, looks like helium. Fluorine has its octet now and looks like neon. Oxygen tends to form two bonds. So this oxygen forms two bonds with something else. Like this one, forms two bonds. Nitrogen tends to form three bonds. And these can come in any arrangement of bonds as long as there are three of them. So for instance, nitrogen could form three bonds with hydrogens. And still have that lone pair. So we have 2, 4, 6, 8 for nitrogen. That's ammonia. Or we could form nitrogen and carbon. That kind of blows away my theory. Carbon likes to form four bonds, but cyanide is, maybe that's why cyanide is so reactive and it's so deadly, is because this carbon needs to form another bond. So what typically happens is you get hydrogen cyanide, which is, like I said, deadly. So there we have an example of oxygen forming two single bonds or one double bond. Nitrogen forming either three singles, a double and a single, or a triple bond. And there's carbon, which has more options. That may be why carbon is the basis of living systems. Okay, how many covalent bonds can oxygen form? Two. Two covalent bonds or 4 electrons. Now there's another odd type of bond that can form. This is more, we know the compounds form, we know the bonds form, and the only explanation is this idea called the coordinate covalent bond. Up to now, we've shared electrons, like an electron from this atom, an electron from that atom for hydrogen forms a bond. But sometimes there are molecules that already have their octet, but they have a lone pair. And another molecule doesn't use any of the electrons it has. It takes both of those electrons from the other one and forms the bond. So that coordinate covalent bond is formed when one atom donates both electrons for the bond. Now, once the bond forms, there's no way to tell how it got there. What we have to do is deduce, explain what we think has happened. And let me show you an example. So here we have HO and Cl. So with this 2, we're supposed to have like that, and then here, here, and here. Okay? Now along comes oxygen. And oxygen has 6 valence electrons. If it wants to form make an octet for itself, it's got to get 2 electrons from somewhere. So in this scenario, those 2 electrons would come from here, and we would form a bond with chlorine and oxygen. Okay. But after it forms, there's no way to tell how it got there. We have to deduce that that's the most likely scenario. to form that molecule. All right, I think we're beating the dead horse here. Right. You either form a bond by sharing electron from one side and electron from another atom, or you get both electrons from the other. And anyway, you end up with a bond, a covalent bond. And like I said before, once the bond is formed, it's indistinguishable from any other covalent bond. This nitrous oxide, N2O, laughing gas, right, is the first molecule, and it's formed from a coordinate covalent interaction, right? Because, well, I erased it. The nitrogen molecule would be like this. It's perfectly happy. But if we bring in an oxygen and it forms a bond there, that's a coordinate covalent bond. Carbon monoxide tends to form 3 bonds with oxygen and 3 bonds with carbon. So we would expect 2 bonds with oxygen and 4 bonds with carbon, but we have those lone pairs. We still have the octets for each one. It's just they don't fit the mold. And carbon monoxide is a dangerous molecule, just like cyanide, and it doesn't fit the mold either. So maybe that's one way of looking at it. If it doesn't behave, then watch out. Okay. Coordinate covalent bonds form when both electrons of a shared pair come from one of the 2 atoms in the bond. Okay. Let's continue with Lewis dot structures. I've thrown a bunch of them up here, but there's a method for creating Lewis structures for covalent compounds. And the simplest way is just to put one up here and go for it. So how about, well, we can use this one. Say, we know this molecule exists, sulfur dioxide, right? Go to white sulfur spring or green sulfur spring and drive down the road, and you might smell some of it. So what you do is you count up the valence electrons that are in that molecule. Sulfur and oxygen are in the same group, so they have the same number of valence electrons. Oxygen has 6, sulfur has 6. So we have 3 times 6 is 18. 18 electrons total, valence electrons. Not total electrons, but valence electrons. And then you have to decide which one is bound to which. Right? It's more likely that it's a symmetrical molecule. And you want the central atom to be the one that's either to the pair, to the left or below. So sulfur is below oxygen. It would be in the center, and you form a single bond between the other molecules. Between the other atoms. Okay. Then you subtract 2, 4. Subtract those electrons. So we have 14 electrons that now need to be distributed. You start from the outside and work your way in. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Until you get an octet, right? 2, 4, 6, 8, 2, 4, 6, 8 on the outer atoms. Then you move inward and say, all right, do we have any left over? Yeah, we've got these 2 electrons here. So we put those 2 electrons right there. Okay. So what's wrong with this picture? Sulfur doesn't have an octet. So how do you form an octet without destroying the octet for the oxygens? You take a pair from either side and make a bond. Okay. So we have a double bond on one side. Like that. And we still have that. So now we have 2468, 2468, 2468. Everybody's got an octet. Okay. The problem with this molecule is we could have gone the other side, put the double bond on the other side. Right? We could have written it like this. Like that. That's perfectly valid Lewis dot structure, both of them. Okay. So there's the second step that I've already shown you. And we've got all but 2 electrons ready to go. So we put the 2 electrons on the sulfur. Now we got to make an octet somehow. Because we've used up all of our electrons, we have to, usually what we do is make double bonds or triple bonds if necessary. Okay. Now the way it's shown in the slide, we're leaving the electrons, the bonding electrons as showing the bonding electrons rather than putting them in lines. I like to do it this way because it's easy to tell which are bonding and which are not. Bonding, lone pairs. All right. So that's an example, and those are the rules for forming a Lewis dot structure for a compound, a covalent compound. We've already done these guys. Hydrogen, that's simple. Fluorine, hydrogen fluoride. Okay. We need a more complex example. Here we go. How about, let's see, we've already done ammonia, and I've shown you carbon dioxide. Let's do carbon tetrachloride. So first you have a bona fide known compound, right? We're not making this up. That exists. So our job is to draw the structure that accommodates that ratio, 1 carbon, 4 chlorines. So how many valence electrons in carbon? Well, you count from the left. 1, 2, 3, 4. It's 4 over from the left, has 4 valence electrons. Chlorine, keep going. Carbon, 5, 6, 7. The halogens, as a group, have 7 valence electrons. So 4 times 7 is 28, right? So we have 32 electrons that have to be placed in this Lewis structure. Which one's going in the center? Well, carbon's to the left of chlorine, so we're going to put carbon in the middle. Okay, then we're going to form enough bonds to accommodate the chlorines. Okay, 2, 4, 6, 8. So we subtract 8 from that and we get 24, right? 24 electrons. So how many more can we put around each chlorine to make an octet? Right, 2, 4, 6, 8. So we have 6 more electrons in lone pairs. 4 times 6 is 24. So that uses them all up. If we just make octets with the chlorines, we use up all of our electrons. Okay? Chlorines have octets. Carbon has an octet. We're done. Okay? Now this is a skill that you need to develop. The reason being that we're going to, from here, we're going to infer 3-dimensional structure. There we go. Right now, we're just drawing it in a flat plane, but this molecule is actually 3-dimensional. Okay. Total number of dots in the Lewis structure for SO2. Total number of dots. 2, 4, 6, 8, 10. 12. Or are they counting? I think they're counting bonding also. So that would be 18. Yeah. If you draw it the way they drew it, with the electron, all the electrons in there. Yeah, total number of dots would be 18. That's actually the proper way to say that is the total number of valence electrons in this molecule. All right, now we got a special case. Polyatomic ions. And I may have mentioned this before, but it may not have made sense then. Hopefully it'll make more sense now. Polyatomic ions are kind of hybrids. They can participate in ionic bonding because they're charged. So we can have sodium sulfate, like that. That's an ionic compound. But this is a polyatomic ion, which has a 2- charge of its own. The polyatomic ions are covalently bound groups of atoms. So this sulfate is a covalently bound assembly of atoms, which happens to have a charge. So here's your sulfate. Let's do the sulfate. How do we get there? How do we get to the Lewis structure for the sulfate polyatomic ion? So we need sulfur and oxygen, same group. So they're going to each have 6 valence electrons. 5 times 6 is 30. But they've got 2 extras. So you have to count the charges. 2 extra electrons means 32 electrons. So don't forget the charge. All right, now that we have 32, which one's in the middle? Well, we do like before. We're going to put sulfur in the middle. We have sulfur, and we have 4 oxygens. So that's 2, 4, 6, 8. 24 electrons. 2, 4, 6. 6 times 4 is 24. We'd use them all up. Okay. Now, there's the Lewis structure, but it's not finished because it has a charge. So we have to represent that like this. And the charge doesn't belong to any one of these atoms. So we have to put it outside the brackets. It's a charge that's assigned to the whole group. Okay. Now, let's see if that charge is correct. Right? How many, if we've got 6 valence electrons in oxygen or sulfur, how many protons does that represent for neutrality? 6 protons each, right? 6 protons each would balance the 6 valence electrons. So we have 1, 2, 3, 4, 5, 6 times, wait a minute, 5 times 6 is 30. So that's 30 protons that will associate with valence electrons that causes neutrality. Right? If we just count up the valence electrons, then the same number of protons will be required to make it neutral. That's why I'm only counting 6 protons for each one of these. So that gives us 30 positive charges, but we have 32 electrons in the molecule, valence electrons in the molecule. So the difference between those two is 2 minuses. That's where that charge comes from. It's an imbalance between the protons and electrons. Now we could do the same thing by counting all the protons and all the electrons. But I think since we're talking about bonding, we're just going to limit our discussion to valence electrons. Now, the proper way to write the compound that they're showing us there is, well, they're using potassium. Sodium will work also because it's a single charge. So we have a sodium here and a sodium here. So the attraction between the sodiums and the polyatomic is ionic. but within the sulfate, it's covalent. That's why I called it a hybrid. Okay, how many valence electrons are present in the polyatomic? We counted those up. There were 32. Okay, molecular geometry. The reason we need to know the three-dimensional structure, or the geometry of a molecule, is that's one of the ingredients for determining whether a molecule is polar or nonpolar. What I mean by polar and nonpolar is similar to a magnet, right? A magnet has a north pole and a south pole. Molecules have a side, sometimes, have a side that's partially positive and partially negative. They have charge separation. It's not a complete separation that would form an ion, but in these covalent compounds, we have a separation of, sometimes we have a separation of charge, positive, negative, and it makes the molecule polar. It has a positive side and a negative side, and that affects how it behaves with its own kind and with other things that you put in solution. So we need to be able to infer polarity or nonpolarity in the molecule to understand how it behaves. To do that, we need to know something about the geometry. And we're going to take the Lewis dot structure and go the next step, which is this model, which is, let's see, I should have written it this way. VSEPR stands for, this is valence, shell, electron, pair, repulsion. That's a mouthful. The main idea behind this theory and the model that forms from it is that when electrons are surrounding a central atom, and for now we're going to keep it simple, right? This will be a central atom and things around it. The electrons, both bonding and non-bonding, are trying to get as far away from each other as possible because they're all the same charge, right? Even if they're in the bond, they still have the repulsive ability for other electrons. Okay, so we try to get them as far away from each other as possible. And to do that, we need to know the Lewis structure. Now, when we work from the Lewis structure to a proposed three-dimensional geometry, we treat the electrons in a bond as a single group. So a double bond would be a single group. A triple bond would be a single group. Single bond, obviously, a single group. Rather than saying two pairs for a double bond and you have to count them separately. No, they're together. They're close enough together in that region between the atoms that we count them as a single unit. Okay. So first of all, we draw the Lewis structure. We've done that. Then we determine the number of electron groups that are present around the central atom. So let's take, let's go back to our sulfur dioxide. Okay. In this one, how many groups or lone pairs do we have around the central atom? We have 1, 2, 3. Right, 3 groups. There are standard geometric shapes that we associate with the number of groups. So let's make room over here. So let's see, the number of electron groups will be in this column. right? And then the electronic geometry will be in this column. So with three groups, let's see, we can have two groups, we can have three groups. We're at three now. The shape that will put these groups the farthest away from each other around that central atom is a trigonal planar or an equilateral triangle. So if we drew it like that, we would have sulfur here, we would have the lone pair up here, right? Then we would have down here, we would have an oxygen, and then over here we would have an oxygen. And that would form the shape of an equilateral triangle. Okay. Now, when we reference these shapes, we're not talking about the bonds necessarily. Right? This is just the shape that it occupies in three-dimensional space, and it's planar. It's a trigonal planar molecule. Now, if we had two, say we had carbon dioxide. Right? How many groups around carbon? Only two. Two is always linear. Right? That's a linear molecule. That gets those bonding pairs as far away from each other as possible. Now, if we talk about bond angles, let's say, let's put bond angles over here. The bond angles are, well, I'm getting ahead of myself. What we need here now is molecular geometry. So what's the difference between electronic and molecular geometry? You just cover up the lone pairs because there's no atom there. Right? So we're trying to find the bond angles, and there's no bond angle here because there's no atom. Right? So we just cover up the lone pairs. So what do we have now? I think your textbook might call it angular. I like bent. This is a bent molecule. So it could be trigonal planar if every position has an atom in it. But in our case, it's bent if we have one lone pair. Okay. How about carbon tetrachloride that we did before? We had carbon and chlorine. Right? How many groups around the central atom? 4. Right? 4 groups. The standard shape that puts these groups as far away from each other as possible is a tetrahedron. And in that case, the molecular geometry is also tetrahedral. Okay. So if we tried to draw that with an eye toward three-dimensional geometry, we would need like a triangle on the base, and then we would need something up here. Right? A triangular-based pyramid, that's a tetrahedron. Remember that from math, geometry? No? Okay. And in the center would be the carbon. So it would have a bond to a chlorine here, and a bond back here to a chlorine, and a bond over here to a chlorine, a bond over here to a chlorine. That puts those chlorines and the bonding pairs as far away from each other as possible. Okay. So if we were to do ammonia, Ammonia would be like this. It also has 4, right? So its electronic structure would be tetrahedral, but it has a lone pair. So what happens if the lone pair is up here? What you have now is a trigonal pyramid, right? With the carbon up here and, well, the nitrogen up here and a hydrogen, hydrogen, hydrogen down there. So with one lone pair, we have a trigonal pyramid. Instead of a tetrahedron. Okay, so I've already given you those, right? Carbon dioxide is going to be linear. It has 2 groups around the carbon. Hydrogen cyanide, also linear, has 2 groups around the central atom. What's that? CH2O, trigonal planar. That's formaldehyde. You ever smelled formaldehyde? No. You ever done any dissections? No? Okay. You don't forget the smell. And then we showed you this sulfur dioxide already, and it has a lone pair, so it has a bent shape for the molecule. Now, the angles that are involved here, what's the angle for this one? 180 degrees, right? Okay. How about, let's see, I erased that one. How about the angle for this one? Well, there's only one bond angle because that's a lone pair, but the angle should be, right, if you add up all the angles as you move around, they should be 360 degrees, right? 360. If you have an angle here, angle here, angle here, go all the way around, it's 360 degrees. So a third of 360 is 120, right? So this would be 120 degrees nominally. What happens is, notice that lone pair up there. What does a lone pair do if it's not confined in a bond? It goes like that, spreads out, which puts pressure on the others and decreases that bond. So it's actually less than 120. How about the bond angle for a tetrahedron? You just have to memorize this one. I mean, if we had time, we could prove it. But the bond angle for a tetrahedron, bond angle here would be 109.5 degrees. The rest of them are logical. That one, we had to calculate it. Let's see, I'm not sure how deep we're going to go into this. Water's a good example, right? If we had water and we did the Lewis dot structure, we would have hydrogens over here and oxygen would have these 2 lone pairs. So the electronic structure would be 1, 2, 3, 4 tetrahedron. But if we cover up the lone pairs, we got another bent molecule. Okay. Now, what does this have to do with polarity? Well, there are 2 factors to consider when you're trying to decide if a molecule is polar or nonpolar. And one has to do here with symmetry. Are the bonds symmetrical all the way around? These bonds are symmetrical for carbon tetrachloride. So any difference in the way they attract electrons to one another is canceled out. Whereas oxygen and hydrogen like this tends to form a slightly negative on that side and slightly positive on this side. And that has to do with a concept called electronegativity. How strongly do the atoms attract electrons in a covalent bond? Hopefully that's coming up. what we're trying to show here is if you have a more complex molecule, you talk about the geometry around a central atom, and bigger molecules can have multiple geometries. But we're trying to keep it simple here with just one central atom and its attached atoms. Let's see. Okay. So we got up to tetrahedral. What if we have 5? If we have 5 groups around a central atom, how are they going to space themselves so that they're as far apart as possible? And this is not just imaginary. There is physical evidence, right? Experimental evidence for these structures. So if you have 5 groups around the central atom, the electronic structure is going to be a trigonal pyramid. Let's see. Let's make some room here. So if you have 5 around the central atom, you're going to have a trigonal bipyramid, excuse me. You're going to have these 3 positions here, and then you're going to have a position up here and a position down there. So we have 1, 2, 3, 4, 5 places. So you're going to have a central atom here, and then whatever. You could have lone pairs, or you could have atoms in each one of these positions. So the trigonal pyramid, trigonal bipyramid, oops. Is the electronic structure, and if each position is occupied with an atom, it's also the molecular geometry. And the last one is if you have 6, you replace that triangle with a square. Have places for 4 here and 2 there. And how many sides do you have? When you have a 3-dimensional object with hedron after it, you're talking about sides. So we have, if we have something here, say we draw an imaginary line there and there and there and there, we have a side here, a side here, a side here, and a side here. That's 4. And then 4 down here, that's 8. That's an octahedron. Okay. Now, I'm not so sure if I'm going to introduce, what do you do if you've got lone pairs in there? Yeah, I guess I did. Okay. We've talked about lone pairs for these. How about lone pairs here? Where do the lone pairs occur? If you have a lone pair in a situation like this, where does it go? Right. The lone pairs or the trigonal bipyramid show up on the triangle, the central triangle. So we would have 1 would be here. Right? If we had 1 lone pair, what would the geometry of the molecule look like? Well, if we drew like that and like that and like this and this, and you turned it on its side, you would have legs here and out here. That's why we call it a seesaw. So 1 lone pair for this one gives you a seesaw. What if we had another lone pair, say, back here? Right? Yeah. Then we would have this one sticking up like that, and these 2 out there. That's a T shape. And of course, if you had 3 lone pairs, it would be linear. Molecular geometry. Let's see. Am I going to go? I want to go backwards 1. Here we go. Okay, that's all I did for that one. Okay. That's probably a little more detail than you wanted. What's the shape for each of the following molecules, and what are their bond angles? Well, if we took hydrogen cyanide, we know that this is 1 electron, that's 4 electrons, and this is 5 electrons, right? Yeah. So that's 10 electrons. Carbon's going to be in the middle. Hydrogen can't be in the middle because it can only form 1 bond. And so that's an easy choice. And then nitrogen is going to be over here. So we got 2, 4. That's 6 electrons that we have to place. So we start here, 2, 4, 6. Okay, we used them all up. Now we need to form an octet for carbon without destroying the octet for nitrogen. So we take that, take this pair here, another one like that, and now we have hydrogen cyanide. Okay, the central atom has 2 groups, and 2 groups will always be linear. So that's a linear molecule, and the bond angle is 180 degrees. Oops, I thought I was going to animate it. We looked at ammonia already. It's a trigonal pyramid, and it's derived from a tetrahedron. So nominally, the bond angle will be 109.5, but with that lone pair up there pushing down, ballooning out, pushing down, the bond angle is actually 107 degrees. It's a little less because of that spreading lone pair. And then ozone. How would we do ozone? This is a real molecule, right? That's the one that gets environmentalists all up in a tizzy. So we have 3 times 6, right? 18? 18 electrons. So just, right. Take your pick. This is actually an element, but it does form a molecule. The name for that, different forms of elements are called allotropes. Like graphite for carbon, one form of carbon. Diamond is another form of carbon. Nanotubes and buckyballs, they're different forms of carbon, right? But they're all the same element. This is ozone. It's another allotrope of oxygen. So we've used up 2. That's 4 electrons. So that's 14. 2, 4, 6, 8, 10, 12. So we have 2 electrons left. We'll put them right here. And so what's the electronic structure for this molecule? Trigonal planar. And trigonal planar means the bond angle is 120 degrees. But what's the molecular structure? Cover that up. It's bent. It would be like this. Okay. And it's actually not 120 degrees. It says 120. It's less than 120 because of that lone pair. Here we go. Now to the topic of electronegativity. The 2 things that we consider in predicting polarity of a molecule is the geometry, which we've talked about already. The geometry of the molecule, geometry, and bond polarity. Okay, so we're going to get into that now. We need to understand what we mean by electronegativity. When covalent bonds form, if the atoms are the same element, there's an equal distribution between the 2. In other words, each atom has a pull on electrons. If they're the same atom, then they pull equally, and the bond is symmetrical. So we have no polarity whatsoever in the diatomic elements. Dinitrogen, dioxygen, hydrogen, any of the other diatomics. those bonds are symmetrical and completely nonpolar, 100% nonpolar. But if we put two atoms together that have different electronegativities, then we're going to get a slight pull from one of them. It doesn't break the bond, but it causes the electrons to spend more time near the more electronegative one. And if you need to, we need to predict the difference in electronegativity. We can do that qualitatively from the periodic table. Electronegativity increases from lower left to upper right. So the most electronegative atom in the periodic table, the element, is fluorine. Right? And the least electronegative would be down in the lower left-hand corner, cesium. And that's typical for metals. Metals tend to have a lower electronegative value than nonmetals. Nonmetals have a very strong attraction for electrons. Metals don't. That's why metals give up electrons and go to a positive charge when they do. And nonmetals accept electrons because of their electronegativity. So if we put two nonmetals together into a covalent bond situation, say we put oxygen and carbon. Oxygen's to the right of carbon. It's more electronegative, so the bond would be pulled toward the oxygens away from the carbon. For instance, if we were talking about carbon dioxide, we represent the polarity this way. The positive end of the arrow shows you which end is losing electrons, and the head of the arrow shows which way the electrons are going. Now, we don't break the bond. It's still a covalent bond, but we tend to give this side a slightly negative and this slightly positive based upon the polarity of the bond. The representative elements, right? The first two columns and the last six columns, they're fairly well behaved as far as electronegativities go. So rubidium is down there in the fifth period is 0.8 on this Pauling scale. Linus Pauling set the scale up, and there's a calculation that you can do to produce it, but that's not important for us. And then fluorine is way up there in the upper right-hand corner at 4.0. So it is much more electronegative than rubidium, say. So if we formed a compound between rubidium and fluorine, it would be ionic. And one of the ways to tell is subtract one from the other. So 4 minus 0.8 is 3.2. That's a huge difference in electronegativity. That bond is definitely going to be ionic. Okay. So the general trend in electronegativity across rows and on columns is that from left to right, the electronegativity increases, and from bottom to top, the electronegativity increases. So if we were to draw a periodic table like that, then electronegativity would increase this way, and it would increase this way. That's why we say, in general, the electronegativity increases from lower left to upper right because of that trend. Now, are we going to, yeah, we're going to explain why. Why does it increase from left to right? Well, if you're in the same period, You're talking about electrons being added to the same shell. The valence electrons added to the same shell. So they're really not that much farther away or much closer to the nucleus. But you're also adding protons. So you're increasing the effective nuclear charge by adding protons. That increases a stronger pull on electrons that are just being added to the same place. So you get a stronger attraction from left to right as you increase the nuclear charge. From bottom to top, what you're doing is, well, you can look at it two different ways. If we go from top to bottom, you're decreasing the electronegativity, but I'm trying to explain it in terms of increasing electronegativity from bottom to top. So what are we doing from each period as we go up? Well, we're decreasing the number of protons, obviously, but we're also decreasing the number of electrons around the nucleus. So what happens when you have a nucleus and electrons around here like that, these outer electrons, if there are electrons between them and the nucleus, they have a shielding effect. So the outer electrons don't feel the pull as strongly. So they're more likely to leave if there's a strong enough attraction from outside. So we reduce the shielding effect as we go up because the electrons are we're reducing the number of electrons that surround the nucleus and shield it. So we get this effect as we move up. The size of the atom is shrinking, and we're reducing the nuclear charge, but we're also reducing the shielding. So that has an effect of increasing the field, the positive field to the electrons that are left behind. That make any sense? Okay. Okay. So if lithium and fluorine react, which element will have more attraction for an electron? So where's lithium? Lithium's over here. Fluorine's over there. So the stronger attraction will be fluorine. So if we have lithium and fluorine together in a molecule, they are so far apart, this is going to be an ionic bond. Right? The strength of attraction from the fluorine is so strong, and lithium has such a little pull on the electrons, it will give up an electron readily. How about fluorine and iodine? Those are two nonmetals. And believe it or not, we can form a bond between fluorine and iodine. So which one has the stronger attraction? Fluorine is above iodine. So fluorine is going to have the stronger attraction. This is still a covalent bond, but the attraction is going to be stronger toward fluorine. Highest electronegativity here, hydrogen, helium, oxygen, chlorine. You can ignore the noble gases for now. Don't even consider them for, because you have to form a covalent bond in order to assess electronegativity, and noble gases don't form bonds, typically. So we just forget those, and we stop at the halogens. Okay, so helium's out. So which one is furthest to the right? Well, it's a toss-up between oxygen and chlorine, but oxygen is above chlorine. I suspect that oxygen has a stronger electronegativity than chlorine. And one of the reasons for that is not only that it's almost to fluorine, is that it's above chlorine and it has less shielding, fewer electrons shielding the nuclear charge. Okay, bond polarity. I've mentioned that before. This is a measure of the degree of unequal sharing of electrons between two atoms in a covalent bond. The greater electronegativity difference between the two atoms will produce more polar bond. So when we're trying to assess the polarity of the whole molecule, we need to know something about the polarity of the bonds, and we need to know geometry. Because even if you have polar bonds, if they're evenly spaced in one of these regular shapes, then they will cancel each other out. Carbon dioxide is like that, right? These are equal and opposite. So carbon dioxide overall is a nonpolar molecule. Obviously, when you have two of the same atoms, that's nonpolar covalent. There's no argument there. A polar covalent is one which produces a positive and a negative side of the bond. Chlorine is more electronegative than hydrogen, so the bond is polar toward the chlorine. We use this little symbol sometimes. That's a Greek delta. Right? Remember, you've seen the big delta like that. This is the small delta in the Greek alphabet. So we use the small delta with a sign on it to show partial charge separations. Now, qualitatively, we've talked about trends in the table so far, but if you know the values, the electronegative values of the two atoms in a bond, you can make a semi-quantitative assessment. All you need to do is subtract the two, and if the difference is less than 0.4, then you have a nonpolar covalent bond. Nearly equal sharing of electrons. If the difference is between 0.4 and 1.5, then you have a polar covalent bond, or an unequal sharing of electrons. Now, the gray area occurs between 1.5 and 2. If the two atoms are nonmetals, then you still have a polar covalent bond. So for nonmetals, between 0.4 and 2 is polar covalent. But if one of the elements is a metal, then from 1.5 on is ionic. And definitely anything above 2 is ionic. You're not going to have any nonmetals bound to each other with anything greater than 2. Doesn't happen. All right. So arrange the following bonds in descending order of polarity. So the most polar to the least polar. Let's see, I'm going to make a little room here. Let's see. I want to leave take this out also. So if we have, for A, we have nitrogen and fluorine, and we have oxygen and fluorine, and we have carbon and fluorine. So we want to go from descending order of polarity. The most polar is the farthest to the right. So we would do like this. Most polar is over here. So which one of these, this is the easy one because we're bonding with fluorine. It's the most electronegative. So which one's closest to fluorine is going to be the least polar. Oxygen is the closest one out of that group, right? Oxygen and fluorine would be the least polar. The most polar would be the one that's farthest away from fluorine in this group, which is carbon. And in the middle is the other one. So that would be the order of polarity from least in descending order up and in ascending order. Okay. Make out like you're reading Hebrew, right to left. So it should be, right. It should be this one first, then this one, then that one, in descending order. Maybe I can get the next one right. So next one we have carbon and fluorine, and nitrogen, oxygen, and silicon and fluorine. Okay, descending order. So the most polar, the descending order of polarity. Yeah, descending order. So which is closest? Now we have a mixture, right? Carbon and fluorine, they've got two neighbors in between them. So that's probably the most polar. Nitrogen and oxygen are right next door to each other. Silicon and fluorine are farther apart than even carbon and fluorine. So silicon and fluorine should be the most polar. Right? And then the least polar would be the next door neighbors, nitrogen and oxygen. And that means this one's in the middle. Let's see if I got that one right. Yeah. Silicon, carbon, nitrogen. Okay. How about the last one? So we've got two chlorines, got a boron and chlorine, and we got a sulfur and chlorine. Okay, so we're bonding with chlorine, each one of them. So which one? This is going to be the least. Chlorine, because they're identical. So what's the most? Which one is farthest away from chlorine? Boron. Yeah, boron's the farthest away. So boron's going to be the most polar. And then what's left over is sulfur. Okay, so we did that qualitatively. So now we're going to complicate things. Which of the following bonds would be the least polar, yet still be considered polar covalent? Okay. So these types of problems, they're like reading the Federal Registry. When a rule is being promulgated by one of the federal agencies, they write this big, thick thing. And the best way to read those is to go to the back and start from the back and read toward the front. Because they always put a summary at the end. So in this case, we're going to look at the back of the problem, polar covalent. So first of all, we've got to find the ones that are covalent. Right? Magnesium and oxygen, definitely ionic. Right? So that one's out. Carbon and oxygen, okay, we can keep that one. Oxygen and oxygen is covalent, but definitely non-polar. So it's out also. Silicon and oxygen, okay, we can keep that one. And nitrogen and oxygen. Okay, so we have these three to choose from. Which one is the least polar, yet polar? The least polar would be the closest together. Let's see, nitrogen. I don't even know that nitrogen and oxygen would be polar. Covalent. Probably that's the one they're going for. Okay, we're crossing out the ones that don't count. Closest together. Okay, that's where we're going. In order to know exactly, we need to compare their electronegativities to see if they really are polar covalent. If they're less than 0.4 difference, then they'd be nonpolar covalent. Nitrogen and oxygen, let's go back and look. Uh-oh, got to go back a little bit more to our table. Oops, went too far. Okay, nitrogen and oxygen The difference is 0.5. So yeah, they're polar covalent. I had to satisfy myself. Okay, how about this? Most polar without being ionic. So the most polar would be the furthest apart without being ionic. So we throw this one out again, and we look at these. Which ones are the furthest apart? And silicon and oxygen are the furthest apart, I think, would be the most polar. Okay. So now, when we're trying to assess the polarity of the molecules, we have to consider the polarity of the bonds and the geometry, because the geometry could cause cancellation. If the polarity of the bonds are equal, but equally distributed in space, then they cancel each other out. For instance, for water, which one's more electronegative? Oxygen. So the polarity of the bond is going to be this way and this way. But notice, being a bent molecule, they're not canceling each other out. They're in fact additive. So overall, the molecule is polar in that direction for the polarity of the bonds plus the lone pairs. So they add negativity to that side of the molecule also. So we considered both the bond polarity and the geometry to determine that water molecules are polar, in fact, extremely polar. All right. There's nonpolar CO2 because the polar bonds cancel each other out. They're equal and opposite. There's water. For hydrogen cyanide, the HC bond is polar toward carbon, but the carbon-nitrogen bond is polar toward nitrogen. So those add up in the direction of nitrogen, and we have a polar bond there. It's linear, but it's polar also. Now, I went too far. We did this one already. Draw the Lewis structure for SiO2. And does it contain polar bonds? Yeah. Difference between silicon and oxygen, polar bonds, and it's bent. So it's kind of like oxygen. Silicon and oxygen forms, well, actually it's the other way. Oxygen is more polar, sulfur. Oh, we didn't do silicon. Silicon dioxide. We did sulfur dioxide. Okay, silicon dioxide. So silicon has 4, like carbon, and oxygen has 6 each, so that's 12. So we have 16 total electrons. Silicon in the middle, oxygen, oxygen. So that's minus 4 is 12 electrons, right? 2, 4, 6, 8, and 12. Okay. Silicon is deficient for the octet, isn't it? So the most efficient way is to do that and that. Now there's a way to tell. We could have made a triple on this side and a single on, and left a single on that side. But there's a way to tell which is the better Lewis dot structure. And I don't think we're going to get into it in this class. It's called formal charge. So just say that you heard the name before and let it go with that. So in this case, oxygen is more electronegative than silicon, but the molecule is linear. So silicon dioxide should be nonpolar overall. Oh, didn't say. But that's why. Now, where are you going to find silicon dioxide? You ever been to the beach? Like, you got squishing between your toes every step you take. Sand. Now, there's some other things in there, but it's primarily silicon dioxide. Which of the following molecules are polar? Well, we throw out the F2. We've already done carbon tetrachloride. We know it's nonpolar because it's symmetrical. Then we have HF. Right? It's linear, but fluorine is very electronegative. So HF is polar. Ammonia has that lone pair, so its bonds are polar, but they're not canceling each other out. So ammonia should be slightly polar, and SO2 we showed earlier is polar. So we should have three of them, shouldn't we? Yeah, those three are polar molecules. Now there's polar and there's polar, right? Some are extremely polar like water, and some are not so polar like ammonia. Which is following as a polar compound. We know CO2 is nonpolar. We did that one already. Water is polar. Methane is like carbon tetrachloride. It's symmetrical, tetrahedron, and it's nonpolar. So beryllium dichloride, that's one we haven't done yet. Well, beryllium's a metal. Yeah, that's going to be ionic. So it's not polar, really. Water's polar. Beryllium chloride is ionic, so we can't call it polar. Right? Polar, the description of polar, nonpolar is reserved for covalent compounds, covalent bonds only. Okay. This is, we covered this in a type 3 compound in the last chapter, right? Binary molecular compounds are between two nonmetals. That's a type 3 compound. And how do you name those? You sort of borrow from the ionic version, right? When we say this one, carbon comes first, like the metal. It's not a metal, but it's named like it. Carbon, and then oxide for the second one. And we have to say how many there are. So we say dioxide. Okay, one carbon, two oxygens, there's your molecule. We use the numerical prefixes because in covalent compounds, you don't have any ions. You can't balance charges. So we have to say how many there are. If we only had like this, like this would be carbon monoxide. This one's sort of dangerous if there's enough in there to drive out the oxygen. This one is extremely dangerous if you just get a little bit of it. Did I describe what happens with carbon monoxide? Huh?
I don't think needed ion.
Yeah. The carbon monoxide would be like this. Extremely reactive, and you breathe some in, and it goes where oxygen should go. It goes straight to the red blood cells and attaches itself to the iron in the heme part of the molecule, and it won't let go. Whereas oxygen will weakly bind to the iron, and it will be released when it reaches your cells, right? Provide oxygen for respiration cells. Carbon monoxide won't. It attaches to the iron and it hangs on forever. So what happens when you get too much carbon monoxide in your system, your cells suffocate at the molecular level. Because if carbon monoxide's there, oxygen's not. Okay. So carbon dioxide, sulfur hexafluoride, dinitrogen tetroxide. You have to practice. And that's one of the reasons I gave you that extra credit, so you could practice. And like I said before, I think I've said this before. If you just go in there and Google the names or Google the formulas and fill it out, you're not learning anything. You're just learning how to use Google. And for some of them, I can tell whether you Googled them or not because of the spelling. Because if you Google something, it's going to come up with the wrong spelling. It's going to come up with probably British spelling instead of American spelling. And if that's the case, I'm going to count it wrong because I know you didn't actually do the naming. And extra credits are, you have to work harder for extra credit. Okay. And those are some more examples. We did, oh, well, these are common names. Water, of course. Years ago, there was a hard copy circuit. This was before computers. So somebody had printed off something and they were circulating it and it showed up in newspapers. The hazards of dihydrogen monoxide. Right? If you get too much dihydrogen monoxide, it could kill you. That's water. Hydrogen peroxide. Right? Peroxide is anything that has that in between. Peroxides. Ammonia, NH3. Hydrazine, N2H4. Where do they use hydrazine? Well, several places, but the Nazis used it to fire up their little rocket planes. And they killed a bunch of technicians with it. It's hazardous. Methane, right? Natural gas. That's the primary component of natural gas. Ethane, not common use for that one. Nitrous oxide, N2O. Dinitrogen monoxide and nitrous oxide are the same names. Laughing gas. And nitric oxide. That's the one that is claimed to be the health benefit for vasodilation and lowering your blood pressure. If you eat those soft chews that are made from beets, they're supposed to cause your body to produce nitric oxide, and that leads through a chain of reactions to vasodilation, reduces your blood pressure. I tried them for a while. They work for about 30 minutes. and then your blood pressure goes back up. So I'd probably have to chew them all day long. Okay, which of the following is incorrectly named? Let's see, how am I doing on time? Okay, we're good. Nitrogen dioxide. First of all, when you're naming a compound, you ask yourself, is it a metal nonmetal or a nonmetal nonmetal? This one, NO2, is a nonmetal nonmetal, so it's a type 3. We name it with a type 3 convention. So nitrogen first, oxide second, and how many of them are there? Nitrogen dioxide. That one's correct. Phosphorus and oxygen, two more nonmetals. So we have diphosphorus pentoxide. That one is incorrectly named. Okay. Phosphorus and chlorine, nonmetals. Phosphorus trichloride. That's correct. SO3, nonmetal. They're all nonmetals. Sulfur trioxide. That's correctly named. And iodine monochloride is also correctly named. So there was only one bad one in that group. Let's see, what have we got here? We must be toward the end of the chapter. An unknown is thought to be an aqueous salt solution. However, it was determined not to be conductor of electrical current. Okay. So it's probably covalent. It won't conduct electricity. you know, you can put a lot of sucrose, table sugar, in water. You can put so much sucrose in water that there's more sugar in there than there is water. And 50-50 is easy to make, right, to feed your hummingbirds. But it does not conduct electricity because it doesn't form any ions. So we've got a non-conducting solution, and we have an analysis where we have 1 carbon, 1 hydrogen, and 3 chlorines. Right? Now, is that okay? So they're claiming that's the molecular structure. Which one of the following represents the Lewis structure, molecular geometry, and classification of the unknown? Okay, if we take that, then we've got 4 electrons, 1 electron, and 3 times 7 is 21. So that's 26 electrons. Carbon's going to be in the middle. Okay, so that's 8. And that's 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. Used them all up. And carbon has an octet, hydrogen has a duet, all the chlorines have octets. So what's the geometry of this molecule? 4 groups, tetrahedron. Okay. So if we have a tetrahedron here, we've got a triangle base, and we've got carbon in the middle, and up here, I'm going to put hydrogen up here, put the chlorines down here. Okay. So we've got a bond here, bond here, bond here, bond here. The chlorines, the polarity is going to be toward the chlorines here, and toward the carbon here. Right? So we've got an overall movement of electrons this way and this way to the chlorine. That means overall, the molecule should be polar. Let's see, tetrahedral, so it's either B, C, or D, right? And is it an ionic compound? No, so B is out. A is out, B is out. C or D, it's a covalent compound, but how do we arrange it? Well, what we have to do is look at the number of electrons around each one. All right. C gives hydrogen an octet. Is that ever going to happen? No. So it has to be D. Hydrogen has a duet in D, and the chlorines have the octets. There you go. Oh, we got another one. A liquid molecular compound is given to you and you are told to handle it with caution. It can cause damage or death if it is consumed in large quantities. If it enters your lungs, if you are hit with a frozen chunk of this material, or if a hot solution of it is spilled on you, it's hazardous. However, this liquid is necessary to sustain life. The liquid is pure molecular compound. That means it's covalent. Has no taste, is known to contain hydrogen and oxygen, and identify the liquid, its molecular geometry, and whether it's polar or nonpolar. Okay. Well, if we look at our selections, we're saying it's water, right? Hydrogen and oxygen. Is it linear or angular? We did it already. It's angular. Right? Is it polar or nonpolar? It's polar. Right? Very polar. That's why you can dissolve so many ionic compounds in it, like sodium chloride, straight into solution. Sugar goes straight into solution. Sugar does it for a different reason, though. It doesn't form ions. So water, angular, polar. That's it, I think.